Okay, so we're back to recording. Let's monitor now what happens when I go to. Let me try to change display to duplicate slideshow. Yep, that's when it goes. No, it's still on. Still on. Monitor this thing here. Let's see. Let's see. All right. So here's back to my example workflow. This is the this is now the space where I identified. Hey, this is identified. Hey, this is pore space. This is grain space. Okay. It's relatively easy for your eyes, but look at the noise here. Technically, it's not an easy job to go from here to here. Once I have this, this is foundation of everything else that I do. And it's actually a very important step. So I could just now quantify porosity, simply count how many pixels do I have here that are white versus the bulk number of pixels. Or I could actually do simulation in this space. Okay. So that can be lengthy, but it can be done, and that's called direct flow simulation. I could also go and further process this image, and steps here will become clear later, but first step would be so-called skeleton of this image that is used for a lot of purposes. I can just kind of visualize if I was wanting to quantify tortuosity, right? How tortuous is the path going from one side to the other versus a straight line? That would be one measure, geometric measure of tortuosity. Beware with tortuosity in petrophysics and otherwise, there's at least 4 different definitions. There's tortuosity for electrical current transport, there's tortuosity in the Karman-Kozeny equation, there's tortuosity in various ways. You should kind of be attuned to, well, how did you define that, or what is the assumption of that tortuosity? So I'm calling it geometric tortuosity. If I just find all of the paths from one side to the other from an image and figure out how lengthy are they versus a straight line, okay? And in 3D, they're typically double the length, give or take. Okay, so it takes 1.8 or 1.7 times or so more to go through one side of a sandstone to another, as opposed to a straight line. Okay? So if I have a fracture, for instance, that's relatively easy, that's relatively straight. So I'm closer, way closer to 1. I'm 1.1, 1.2. So that's something to think about. Okay, so I extract that, what we call a backbone or a medial axis. And then using that medial axis here, it's colored in nice ways. So it's kind of going through the middle of my porous medium. And after that, I can use medial axis to find where individual pores and throats are. And individual pores and throats is something that we often use related to MICP measurements, for instance. However, it's not so easy to define, especially not in a general 3-dimensional image. But assume that we can. So for instance, here, I kind of like put here as a throat constrictions. So this is my throat. I put it here as green, and then another throat here, and another pore throat here, and another pore throat here. These 4 throats together with grains kind of delineate a pore, a larger opening. Okay? And that pore is next to this pore. And here you can actually see on top of medial axis that is in red, I have these sort of like pink, magenta colored features. And they're actually what I refer to as throats. And they happen to be identified by a software. And this is how I spent half of my graduate school looking for these in a sense. Though. So essentially, this is a pore throat. And now I can actually organize this pore, this pore, this pore, this pore. They're linked through, and I can organize them in a so-called pore throat network. That I can then use simplified formulas. So for instance, I can assume, even though that's really just by looking at this image, never really the case, I can assume that I have a pressure here, I have a pressure here, and I have a sort of a tube. This throat constriction can be simplified to a cylindrical tube that is as tight as the tightest spot. Okay, and for tube, I've been through my fluid mechanics class. I know what a flow through a tube is and what a flux through a tube is. And I can assemble all these tubes and how they connect. And at each pore, whatever comes in has to be what comes out. I know how conservation of mass works. Okay? And basically from that, I can actually do a speed up my simulation or transport through this porous medium. That's the idea of pore network modeling. Most of the companies that you were on the list, so some of you looked at IROC, there was the former FEI that acquired initial company called Numerical Rocks. They're based on selling you pore network results of pore network modeling. And it's faster, so you can do many more scenarios. Pore network modeling is not just about single phase permeability, which is what I described here, but the essence is the same for multiple phases too. So I call that semi-upscaled simulation after you have this pore throat network. Right? So this is a faster, so if you were again putting together a company, then basically working with a workflow that doesn't need parallel simulation resources is probably a good bet. So a lot of companies do this part, but a lot of them do actually this. So Ingrain, for instance, does direct flow simulation. Okay. So one can also characterize fluids or whatever phases, mineral phases that you have in the pore space. And this is a little bit of history again. This was a software. Right now it exists if I give you the software. But it's software that I worked on, and that was at some point the only free software for this type of analysis of images. And it's something that I worked a lot during my PhD. So basically, if you have fluid phases in the pore space, so this is that same polyethylene imaged at a different time, okay, during a sequence of displacements. And in that particular point, we have residual oil fluid, oil in the pore space, right here, right here, right here, right here. Okay. So then you try to basically identify where those phases are, and that's also a segmentation problem. And you can now quantify fluid saturation on the pore scale, okay, directly from images. And this is a possibility or ability that showed up roughly in 2001, 2002. And from there, you can verify, you can also use images like this against simulation. Today, it's 2020. The latest and the greatest in this is not just identifying fluids in one static configuration that is imaged while static, but actually imaging displacement as it happens. Okay? So that's the sort of in time. The images that you get out that way are humongous because they have time resolution in addition to space. But that's what's the latest and the greatest in 2020, and does require advanced imaging, typically at synchrotron. So those are the light sources that are way more powerful than we can keep in this building. Okay. This is the tomographic view of my PhD thesis, half of it. I was analyzing experiments of fractional flow through that polyethylene core. You can see basically 1/4 of it here. You can see ring artifacts that are pretty prominent close to the center. So I basically spent analyzing, so there was actually 14 of them in the view, but here there's just some of them. So after injecting 0.5 pore volume of water, you get water that displaced some of the oil. This is still oil, this is polyethylene. Then you keep increasing pore volumes of water and injecting more and more. Ultimately, even after 64 pore volumes, which is something you can do in the lab, not necessarily in the field. I don't know how much you would have to inject and for how long to inject 64 volumes, but that's the whole point of a lab, right? The point is that even after injecting 60 pore volumes, good luck to you, there is still some residual oil left. okay? And this is where we do EOR. This is without EOR other than fractional flow, okay? Now, basically, to quantify anything here, you have to identify where those oil and water is, and this is basically red is oil. You can also see that I applied mathematician by trade. It did not occur to me to label oil as green because green is money. That just did not click, and I was designing this color scheme. So here we are. I have oil is red and water is green, but oh well. So this is basically the segmented view of the injection. There are some problems with actual this orientation. We could never actually, you will see some coding here that shouldn't be here. This is actually the artifact, but this was an interesting, the only thing that I could identify later is that polyethylene swelled up with some of the oil. And that we didn't know. We assumed that solid phase polyethylene is static. But I could never perfectly align solid phases that were identified in all of these images. And a whole lot of my PhD thesis was trying to make up for that in making sure that my analysis is not dependent on that. And it looked nonlinear. I couldn't, that's called registration. I couldn't register things by any known means. I kind of tried to optimize it and do the best I can. But what we realized later after I graduated is that it must have swollen up, and we didn't account for that swelling on the core scale. Anyway, that's an interesting aside. So you will a lot of times capture in images something that you don't think about, and that people often don't think about in core scale experiments because they don't see inside. So once you start looking inside, you can see a lot of things that you don't necessarily expect. Okay, so that is the small scale. Here I had all of the detailed views of the fluids. On a larger CT scale here that exists in Dr. DiCarlo's lab, this is an image from a student that just graduated, Hassan Khan, and it's available if you follow this link on DigitalRocks portal. This is an image of sintered bead packs. So these are glass beads. And there are vugs within that he created himself to study the vuggy, sort of a proxy for a vuggy carbonate. Now, you don't see the details here in the pore space. You see details of the vug because these are 1 millimeter beads and the resolution is fraction of a millimeter. So not enough to resolve all of the pore spaces between. That's important. You have to know what is the scale of your image and what you can see versus what you cannot. So basically, this would be what we would call as pore scale because I can see, or grain scale, I can see individual pore and grain just as a matter of definition. And this is sort of a core scale where certain things are averaged. So how do you actually get to the log scale that is averaging over a foot or so, right, is an entire different matter. Okay. And speaking of multiplicity of scales, this is, I think I showed this already, but this is how shale looks like. If you image a core, maybe you see some fractures. Okay. Is this a natural fracture or not? You see the details of this line? Sometimes processes in the lab are fast, but for the most part, cement will not show up during the time of your experiment. Therefore, the cement was there before the image, therefore that fracture is likely open or kept open with cement. It's one way. Sometimes there are some experiments that are fast enough that this can actually happen while you're doing the experiment. But for the most part, you can kind of open a fracture to see if it's freshly open, so that means that it's open while you handle the core, versus the ones that's in situ. And geologists, structural geologists, typically looking at the core when they're assessing whether the core is fractured, because that's an important part. These type of fractures, they're not seen on metal logs. So a structural geologist has to look at the core to see whether they exist. Whenever you average something like this 7 millimeter, it's not going to show up on a metal log. But it's good to know whether the system is fractured for permeability for sure. Okay, so when I zoom in, you can actually see, so this is moving in these blocks. You actually have to get to good nanometer resolution scale to actually see pore systems. And this is done with microscopy. And this image is pretty large. It's a tiled image. I think I commented on it already. All right. So one workflow or research objective, this is from the flow perspective, but really it matters on what it is that you want to model, is to do experiments and image them, and then characterize the core itself and the pore space or solid space that you're interested in. Possibly if you have multiple phases in your image, they could be mineral phases, it could be fluid phases, you characterize them as well. And you can, since you image an experiment, you can use those as validation of whatever simulation that you're trying to model, or the type of modeling. So basically you can verify whatever you use this image as an input for and what you see in experiments themselves. And then you ultimately, either way, want to predict macroscopic flow parameters. And the whole point of developing a model that matches experiments is to then use that model in situations that you don't have experiments for. Okay? So in this case, for instance, you could model relative permeability, but you are possibly interested in some different other. Okay, so just a quick review. This procedure, this is a tomographic image. This procedure of identifying different phases in this image is called segmentation. After the segmentation, so I identify, I can do which type of simulation? Direct simulation. Or I can further find medial axis or whatever is the way of finding pores and throats. And after I have a pore throat network, I can also do sort of semi-upscale simulation. So pore network modeling is sort of a faster way to model. So basically you're going to assume that instead of this pore, look how difficult it is, right? And this pore is difficult. You're going to assume it's a simple geometric object. And that simple geometric object has a flow or flux description. So if I'm thinking about modeling flow, I'm going to assume all of these objects to be cylinders because I know a quick and fast estimate for a flux through a cylinder. I have a formula for it, theoretical formula. And then you're going to assemble those objects into a network and flow through a bunch of tubes. And that can be done we're going to go into details of that, but that can be done way faster than simulating directly in every pixel of this image. They are different. So basically, it's basically as different as flow through a tube versus an object that has a rather complex cross sections. Yes. It's been quantified. But essentially, I would put it this way. For single phase permeability, all is well. Most of the flow really goes through that middle. And whatever inertial stuff you have happening near the boundaries, it's so slow that it doesn't matter. Where it starts mattering is for two-phase flow, where it's that inertial stuff and stuff on the side that ends up trapping fluid. And one thing that these poor network models have trouble doing correctly is capturing residual saturation correctly. Because these objects, these cross sections are oversimplified. So that's essentially what it comes down to. I mean, you could open a philosophy club, but all of the modeling ultimately is making some sort of error, right? And you have to choose for the process that you want to model, how comfortable are you with those things? So again, but sometimes the problem is that if I can, let's say that I can simulate all of the details, but if it takes me so long that, let's look at it through a student eyes. So if you can do only 3 to 5 simulations by the end of your graduation, right? You can't make conclusions. We have to be able to compare a number of things to actually conclude something. And your model has to be just as good to capture the difference you're interested in studying. So your model has to be sensitive enough to capture the difference you're interested in studying. And then it's useful. It can be oversimplified, but then it's useful if it can capture it. Right? This comes from a person that loves spending 2 weeks on simulation per time. But I'm just telling you from the practical perspective. That's my interest, research interest, is going after things that are difficult, so to speak. And I think that's frustration that my students might have, Smile, is that they don't get to do a lot of fast simulations that take 8 minutes each. But at the same, that's a research objective. But there are certain things that you can't capture with oversimplified. But there are certain things you can. So your model should be complicated, but not more complicated than it needs to be, which is there's a whole art in figuring out what that is, right? And what is the good, and is the method that you're interested in practical enough? And again, the poor network model, they're becoming better and better, and fine-tuned and fine-tuned. But then it becomes, by the time you fine-tune them, they're a lot of work, and they're not as simple anymore, right? So it's all a balance. All right. So why would you go through the trouble? This characterization of fluid and solid phases can be pretty cumbersome, is because you can gain fundamental understanding and you can zoom in. And I think that is valuable to zoom into the transport processes without basically losing the details that you have to lose if you're just doing experiment and you can't look inside. So this enables you to look inside. And this process, I think that's how we proceed. We have to move everything along. They never take it that like you can just do imaging or just do one type. We have to move along all types of investigation. They're all on different scales, typically capturing different things, and in comparison is when we learn, essentially. And that can then help in well log interpretation. Well log is practical on the well scale. There's nothing that we can do. We're not going to be able to zoom in into a centimeter, I don't think, in any near future. But so we have to average things over a foot, but this constant comparison between different scales will help in that process. All right, so often we will use mixing rules in well log interpretation, but the reality is more complex. So the objective of this review in this course is to understand the basics of image analysis for porous materials and any related modeling, get some practical experience in those, and figure out where you want to go if you want to further study for something that you're specializing in. And also to become an informed user of software and kind of figure out what's typically going wrong behind the software solutions so that you are better off figuring out what to do. Now, this started my first short course, and I was the first person to do a short course on this topic was in 2011. And I had also a workshop with a lot of invited speakers. Then I had a short course affiliated with different conferences together with Drs. Wildenschild from Oregon State and Shepard. Since then, these materials have quite evolved. This is the third time I'm teaching this course as a full semester course. I've taught a number of courses for industry and so forth. So these materials have been worked with quite a bit. If you're interested in reading, gentle introduction, light reading is Russ and Foss. He works for JPT, Journal of Petroleum Technology. So he kind of like does a light version of a lot of scientific studies to introduce people into new technologies. So there's a 2011 and 2017 paper there. There's a review paper on imaging and modeling, which is by Blunt in 2013. He has since written a book. I have a book in my office if you're interested in looking at it. It should be available in the reading room here, the reading room at Petroleum Engineering. Okay? And then there's some of these review papers that we will bring up as we go. And this is the paper from my PhD that I showed the results of. If you're interested in petroleum industry perspective, so I asked you to actually kind of look at what companies offer as a service. Now these are essentially identified from BP, Statoil or /Equinor, they changed the name, and Chevron. You can see how this is a relatively short paper from Chevron where they basically use DigitalRocks technology for quality control in assessing relative permeability. Okay? So this can be like sort of a practical, how does industry use these results? And then yes, DigitalRocks portal was also featured in JPT in 2017. So you can, but Trent Jacobs was the writer. And there was one of the projects on the ERP that was mentioned. Okay. All right. And I actually have an industrial research program on this topic, or I'm in the process of starting it up. And there's links to the YouTube videos that can review like some of the research that is going on in my group, if you're interested. So basically, you can take a look at some longer presentations on some of the topics that are relevant, essentially relevant to improving relative permeability description and electrical properties in heterogeneous porous media. Good news is that this video is still going on for now. I hope I didn't jinx it now. Let me switch a presentation and let's monitor that it still goes on. Okay. So I'm going to switch to the next lecture. I have asked you all to bring a laptop. I hope we actually get to, in the next half an hour, start doing things, though I'm going to introduce some of the images. So this is a new presentation, but has everybody installed Fiji on their laptop without any problems? Or possibly you don't know that you have trouble right now. That software has been behaving pretty well on different type of hardware. The only problem that shows up is the limitations in memory. But that's more of a, if you have too large of an image that you're trying to open. Did it?